Dementia is a debilitating disease that gradually robs patients of their cognitive functions, including memory, their capacity for learning, and language. In Alzheimer's disease, this is in part due to the brain atrophy associated with the disease. As the most common form of dementia, AD accounts for up to 70% of dementia cases, resulting in a major burden on healthcare, society, and economies. Alzheimer's disease was first discussed in 1906. Since then, several hypotheses to explain its origins have been proposed. The amyloid hypothesis remains the leading proposed mechanism, in which plaques formed from the accumulation of amyloid beta peptides in the brain are believed to be the cause of AD pathogenesis. However, anti-amyloid therapeutic strategies have yet to translate into useful therapies, suggesting the amyloid beta protein and its precursor, the amyloid precursor protein APP, are but a part of the disease cascade. The tau hypothesis, on the other hand, lays blame on the formation of neurofibrillary tangles from the abnormal phosphorylation of the microtubule-associated protein tau. Recent reports suggest that both of these mechanisms may actually coexist in a synergistic manner. In addition, several other factors are known to affect the risk of developing Alzheimer's disease, the largest of which is the presence of the E4 allele of apolipoprotein E, or apoE4. apoE4 is part of a family of polymorphic alleles of the apoE gene, which also includes apoE2 and apoE3. While apoE3 is the most common allele, only E2 and E4 are linked to AD, with the former conveying a surprisingly protective effect. apoE4, on the other hand, dose-dependently increases the risk of Alzheimer's disease and lowers the average age of disease onset in non-familial AD individuals. Its influence is believed to involve both amyloid-dependent and amyloid-independent mechanisms, making it a complex risk factor that has yet to be fully understood. In the amyloid-dependent mechanism, apoE4 is believed to affect the level of A-beta aggregation in the brain, as well as its clearance. The binding of lipidated apoE3 to soluble A-beta facilitates the clearing of A-beta across the blood-brain barrier. Lipidated apoE4 binding to A-beta, on the other hand, is not carried through the blood-brain barrier as easily. apoE4 can also bind directly to A-beta to form insoluble A-beta plaques, further worsening the level of A-beta accumulation. apoE4 can also exert influence in an A-beta independent mechanism. It is also associated with cerebrovascular disruption. Astrocyte-secreted apoE4, but not apoE3, activates the matrix metalloproteinase, or MMP pathway, which then breaks down the basement membrane and tight junctions, resulting in the loss of tight junctions and the accumulation of toxic substances in the brain. In this recent publication from Thomas Sudolph's lab, they implicate a novel direct action of apoE4 on APP transcription. apoE4-treated neurons triggered the greatest increase compared to E3 and E2 in A-beta production, while the interaction of apoE4 with its receptors blocked proteasomal degradation of the MET kinase, dual-leucine zipper kinase, or DLK, which is associated with axonal growth and neuronal degeneration. This triggers the MKK7 cascade, thus increasing APP transcription and ultimately A-beta levels. This is a significant new theory that highlights enhanced APP transcription and A-beta production as a novel gain-of-function effect of apoE4 towards the pathophysiology of AD, in addition to its loss-of-function effects. While this is intriguing, it raises many more new questions as to what other factors may be involved in defining the pathological role of APP in Alzheimer's disease. Thank you for listening to our video. For a more in-depth discussion of these topics, please check out our review on BioEssays.